let us continue our afternoon session, and it's my great pleasure to introduce the next speaker, Athanas Papadopoulos from the University of Strasbourg, and he will speak about some rigid actions of mapping class groups.
Thank you. Thank you very much. I'm very pleased to be here again. I came here several times. The first time was 1991. I think several of you were not born at that time. I came here for a conference, in fact, dedicated to A.D. Alexandrov. And then again, I think maybe 2 years after, there was a conference dedicated to Alexandrov and Buseman. And Buseman was here. It was the first time I see Buseman. And then I came several times, in fact. I come here obviously because I like this city, I like this place, I like to hear Russian, I like the museums here, and okay, so I gave I gave a title which is very generic, in fact, and I was not sure when I gave it what I'm going to talk about. And yesterday evening I started preparing. I was a little bit panicked because I didn't know exactly until now. I don't know exactly what I will tell you about, but it is about actions of mapping class groups, like it is written here. There are several options, in fact, and let me make a list of a few actions of mapping class groups. So maybe first I make a list of all these actions which I like, in fact, which these are results which I obtained either myself or with co-authors, and many of them are with Kenichi Oshika. So we started collaborating in, I think, in 2018 or something like that. First, he improved a theorem that I proved, and then we became collaborators, and I see him several times every week. So if I forget to say the name of my collaborator, this is the main one. And okay, so let me make a list of what are these actions. Of mapping class group. So I want to consider a surface closed of genus greater or equal to 3. So and the mapping, when I say mapping class group, I mean the extended mapping class group. The extended which means that I allow orientation reversing. So yes, okay. So closed of and this is oriented. I want it to be oriented also. Orientation reversing map. homeomorphism. And I will make it act on several spaces, and I will tell you what are these spaces now. I have to understand how this works. Okay, so the first action is on ML of S. This is the space of measured geodesic laminations. I will say a few words about this. I never understand how this works, because how do I write on the next one? Okay. I switch. Okay. Okay. So I will recall what is the space of geodesic laminations. I will try to explain. The important thing is that this space carries a piecewise linear. Well, it is natural in several ways. Let's put it natural. Natural structure. Natural, you can understand it as invariant under the mapping class group. The mapping class group acts piecewise linearly on this structure. And in fact, the first result I want to state, and probably I will explain it a little bit. So the mapping class group, I will call it gamma of S. I said natural because it's the mapping class group acts on this, preserves this piecewise linear structure. And so there's a map from gamma of S into, and this is the PL automorphism. The PL automorphism group of measured lamination space, the piecewise linear automorphisms of this structure. And in fact, this map is an isomorphism. There is no other piecewise linear automorphism for this structure I'm talking about than the one coming from the mapping class group. And in fact, I said that I want for this and for all the other results, I said that I want G greater or equal to 3. In fact, in the case G equals to 2, this map is surjective, and the kernel is just the hyperelliptic involution. But I don't want to talk about this special case. And there are special cases also for surfaces, boundaries, and so on. But this will be a distraction. I want just to consider the cases where this map is this map is the automorphism group of this structure. So this piecewise linear structure, in fact, is very rigid. In fact, you cannot break it everywhere. In fact, I mean, because a priori you can say, okay, piecewise linear, then I cut here, I cut here, I cut here, but no, this is a rigid structure. So this is the first result. Now I want to talk about other results like this. So the second thing I want to talk about is again this space of action of gamma of S on measured lamination space. So a measured lamination is first it is a lamination. So it's like a foliation, but the support of the foliation is not all the I mean, it's just a subset of the surface. It cannot be the whole surface. If you are not familiar with this, you see, if you have, I'm talking about a surface equipped with a hyperbolic structure. When I talk about, so these are geodesic laminations. So I should have said this for my first theorem. This is a closed subset of the surface. Which is a union of, well, geodesics. So, for instance, on your surface, hyperbolic surface, you know that you have closed geodesics. This union of closed geodesics is an example of a geodesic lamination. It's very difficult. In fact, it's impossible to make it as a foliation. You see, I mean, you can try whatever you want. This closed curve is unique in its homotopy class, so you cannot foliate like this. And also, while there are geodesics which can spiral here and spiral here, but this is a lamination on the surface. This is a lamination on the surface, but you see there's a lot of free space. There's a lot of space where there's no leaf of this sort of foliation. This is a foliation of some closed subset of the surface. So, okay, a club which is a union of geodesics. And now this is a measured foliation. Measured foliation means that each transverse arc, you can say it's a measure. This is a transverse structure of foliation. There's a transverse measure. Well, there's a measure on transverse arcs, which is invariant when you move the arc by keeping every point on the same, well, leaf. I call it, there's a notion of leaf like in a foliation. So there's this arc here. If I move it a little bit by keeping each point on the same leaf, the measure should be the same. Okay, but in the example which I gave here, you will see that there is no possible measured. There's no possible transverse measure. There's no because I told you that I'm taking another geodesic which spirals along this arc, which means that if I take an arc like this and I make one turn, it will come back to a subset, a strict subset of the arc, so the measure cannot be preserved. So in particular, the measured foliations do not allow such spirals. Okay, so if suppose I have suppose I want to extend this measured foliation, so what do? I can add this as a closed geodesic and this as a closed geodesic. Then I cannot do anything. In fact, I cannot add anything inside if I want a lamination with a transverse measure. But if I don't add these, then inside this surface here, a torus with two holes, there are a lot of measured laminations which I cannot draw now. It's difficult to draw, but there are measured laminations which do not spiral along the boundary. They wander inside. They wander inside the surface. Okay, so a measured lamination, in fact, I say foliation. A measured lamination, so a closed subset of the surface, which is a new union of geodesics. And then there's a measure of transverse arc invariant when you move the arc, keeping each point on the same leaf. And there's a space, there's a space equipped with a topology. This is the space of all measured lamination. With a topology. The topology, you can understand it like, okay, the topology, I mean, very, very naturally, the topology, two measured laminations are close if their leaves are almost parallel, and if the transverse measure induced on transverse arcs are almost the same. Okay, you can take it this. You can take it. Okay, so this is, and then you get a space, which is measured lamination space. This is a famous space which was introduced by Thurston in the end of the 1970s. So, well, and there's an intersection function. Between measured laminations where, okay, when you have two measured laminations on the surface, if they are, these are geodesics. So if they start to be the same, then they will continue to be the same, right? I don't. To compute this number, I don't consider the parts of the surface where they are the same. So if they are not the same, they are transverse, and then there's this. There's a transverse measure here, a transverse measure here, so there's a total measure. So I take, well, the product measure, the total measure of the product measure, and I find here a number. So there's a so this is my intersection function. For instance, let's take a smaller surface just to be short. For instance, I have this closed geodesic, which is a geodesic lamination, and I want a transverse measure. So here the transverse measure should be invariant. So I just choose a number A, strictly positive, and I say that well, the transverse, the measure of this transverse arc is A. If A cuts it 2 times, then it will be 2A. The transverse measure of this associated to this simple closed geodesics is determined by one positive number, which I choose. And okay, this is another closed geodesic here, and suppose I associate to it number the positive number B, then the intersection number here of these two elements will be well 2 times AB, 2 times AB. Okay, and something which is part of the theory, which I'm not telling you, is that this intersection function, which I told you for 2 numbers, for 2 simple closed curves given by these 2 numbers. So there's an intersection. There's an intersection function defined on the product space. Well, which is which is continuous for the topology which I told you, the topology on measured lamination space. So this, I said all this because I want to state the next theorem. The next rigidity theorem is so there's a group of I told you that there's a topology on this space of measured lamination. There's a group of homeomorphisms of measured lamination space of S, and naturally everything. I mean, the things which I said showed you that there's a map from the extended mapping class group to this group. Mapping, everything I said is natural, so the mapping class group acts on this measured lamination space by homeomorphism, and it preserves intersection number. And the next theorem is that this map is also an isomorphism. So there are no, in particular, there are no homeomorphisms of measured lamination space that preserve intersection number, which do not come from the action of the mapping class group. Yeah, sorry, yeah, you are right. A group of homeomorphism, yes, which, yeah, I said, but I didn't write it. Sure, which preserve intersection function. Sorry, thank you.
We consider the full laminations that split our surface into triangles.
Yes. Yes.
So intuitively, our lamination is just several ideal hyperbolic triangles embedded there.
Yes.
Geodesic
yes. Yes, exact. Yes. Yes, exact. Yeah, they can be ideal triangles or ideal polygons. Yes, yes. In fact, they can be a little bit more complicated than ideal because you see, for instance, okay, these closed curves are not ideal. Not ideal. I mean, the complement is not ideal triangles. But okay. I mean, you see the complement. The complement, when you cut the surface along a geodesic lamination, it is something like so whatever. So there are closed curves, and the rest are so okay. Maybe the best thing is to look at the universal cover. So at the lift of the geodesic lamination to the universal cover. The components are always ideal polygons, which could be triangles or more complicated than the triangles. But if it's an ideal triangle, then it's sure that it embeds, the interior embeds in the surface. If it's an ideal polygon, which is not a triangle, it can embed in the surface, but also it can be non-trivial covering of this component, which is not an ideal triangle. Yes. So yeah, it's good to imagine the complement as an ideal polygon, or a little bit more complicated. So, okay, so this is my second you see, and there's a space. There's a space called PML. Well, let me remind you also that ML of S for a surface of genus G. ML of S, this is also something not very difficult to see. Maybe I will show you later, but this is homeomorphic to R to the power 6G minus 6. And you have projectivide measured lamination. So this is when you consider the measured lamination equipped with a transverse measure, but up to a constant, up to multiplication by a constant. Okay? This becomes homeomorphic to 6G minus R to the 6G minus 7, and this is an important space because this is called projective measured. Sorry. This is a sphere, and the first one, I don't want it to be homeomorphic to R 6G minus 7, but well, minus 0, because I don't want to consider the 0 measured foliation. So there's an action of the real numbers on this. We get this sphere, and the projective measured foliation space. Well, this is Thurston's boundary. You are right. I don't want to use foliation. Thank you. I want to use lamination. Thank you. Okay. Who said this? You said this? Okay. Thank you. Thank you very much. The projective measure. Please correct me if I do things like that. So projective measure lamination, and the first classification of mapping classes comes, the initial version comes from the analysis of the action on this first on this action on the space, on Teichmüller space union on the boundary. This compactification. So this the space union. This is the space union about the boundary. I'm not going to do this to tell you exactly in proper words, but either then there's either measured lamination which is preserved on up to a constant multiple, or there's a point in Teichmüller space which is preserved. So in this case, the mapping class will be periodic. In this case, the mapping class will preserve measured lamination up to a constant multiple, but if we forget the measure, it preserves a measured lamination. So either this measured lamination is a curve, as I said, and in this case, the element is called element of the mapping class group is called reducible if there's a closed curve in this, or it's not reducible, so it's a little bit more complicated. This is Sodano. So several years ago, this was very, very, very common. Now I realize it has. This common knowledge has been replaced by other common knowledge, but that's it. So why am I doing this? Because I want to state the next rigidity theorem. So, where is this? So I consider the group of homeomorphisms of this projective measured lamination space. In the previous case, I considered homeomorphisms of measured lamination space with preserve intersection number. So there's no intersection number on the projective measured lamination space, but I can say whether the intersection number is 0 or non-zero. Well, let's say homomorphism H such that H of mu1, mu2 is different from 0 if and only if, intersection number of mu1, mu2 is different from 0 if and only if intersection number of f of mu1, f of mu2 is different from 0. Of course, the mapping class group acts on this projective space, as we said 1 minute ago, and because it comes from a homeomorphism of the surface, so it preserves, it satisfies this condition. So you have this map. Sometimes it's always extended mapping class group. So in principle, I should always put a star, but I'm not putting it. So this natural map is an isomorphism also. This is another another theorem. So, okay. Let me state now still another theorem. Now, this theorem is about unmeasured geodesic lamination. So there's a space called unmeasured geodesic lamination. It does not mean that I'm considering geodesic laminations without the transverse measure. I'm considering measured geodesic laminations, but I am forgetting the transverse measure. This is a highly non-Hausdorff space. I let you think why non-Hausdorff space. And sorry, so this is equipped with the quotient topology. So I am forgetting the transverse measure. It's very different from the projective lamination space. You see, I told you there's a simplicial structure on measured lamination space and some measured lamination. Some measured lamination carry, well, they can carry many transverse measures. Which are not multiple of each other. Okay, which are not multiple of each other. It's not that. So here I'm not. When I'm taking the quotient, it's not that I'm taking. You see, these are. Non-uniquely ergodic foliations. And the space, there's a simplex of a positive cone of transverse measure which they carry, and this measure, the dimension of measures can be up to dimension half of the dimension of the space, 3G minus 3. So all this I'm contracting to a point when all these I'm contracting to a point. So I forget the transverse measure of any foliation. I get a non-Hausdorff space, and then of course, like before, I get now the mapping class group acts as before, and I get a map from here to, well, to the homeomorphism group of, how did I call this? Unmeasured geodesic lamination. And this map is also an isomer. Yes, 1 minute. I have around. Yesterday I was a little bit panicked because I didn't know what to tell you, I mean, how to choose. So I chose just to make you the list of all these things. The list is here. I said less than half of the list. And then I was going to prove one of these theorems, but I speak very slowly. In fact, this is, okay, so this is also, this is also another rigidity result. So you see, I mean, the rest are different variations on the same theme. So the mapping class group, I mean, what I wanted to show this pattern, you know, where the mapping class group, now you can say, well, the mapping class group is a homeomorphism group of some space. And this space is here. This space, as I said, in fact, you have to contract to a point some, the space of geodesic laminations is a manifold. So its space of homeomorphism is, I mean, continuous group, in fact. This space here, unmeasured geodesic lamination, because its homeomorphism group is, well, it's a countable group, means that this space is very, very non-homogeneous, in fact. It doesn't contain any subspace which is a manifold, because as soon as you have a manifold, well, the homeomorphism is continuous and so on. So this is so. So during the last, I mean, one of the things I was thinking about during the last 15 years, each time, okay, what could be a new incarnation of the mapping class group as a group of. It's a group of homeomorphism, a group of bijections, a group of piecewise linear homeomorphism, a group of maps which preserve some linear functions. There are other things like, in fact, when you read Thurston's notes, then you get, I mean, his notes on the geometry of topology of free manifolds. So you get some ideas about what you want to prove. For instance, at some point he introduces a new topology on the space of. I said, what is a topology on this space of measured foliation? He introduced a new topology on space of laminations other than this one. Then you try to prove, you say, okay, so maybe there's a rigidity result here, and then you try to prove what is the structure that I can say I want to preserve. And then I mean, several times. Let me just finish by this. You see, when I prove a rigidity result like this, it's always the same pattern. I want to characterize what happened to, how are the simple closed geodesics in this space, or simple closed curves in the surface, if I forget the hyperbolic geometry. So there are simple closed curves here, and so they have something special for this. For this action, and after simple closed curves, you want to study systems of homotopy non-equivalent simple closed curves. So this, you make this group act on this, on what you find here, and you use Ivanov theorem for the, I mean, there are 15, maybe 15 theorems like this, where at the end I rely on Ivanov's theorem on the, which says that the automorphism group of the complex of curves is the mapping class group. So I said this because Ivanov was here, was working here, in fact, until I think the year 1993. I think he arrived to France in 1993, maybe 1992, but yeah, 1993. It's sure he was in France, and this was the time. This was the time when he proved this theorem. So I learned this from him when he arrived to France. And this is okay. Thank you. Yes.